So welcome to lecture 4. We finally have gone past the math review almost. So a couple things to mention. There actually will be a tutorial today. It's at 4 o'clock. Once again, it's going to be recorded, which means you don't really miss anything by not coming. But during the tutorial, I'm going to go over some math review stuff and some probability review stuff, basically covering like examples of what we saw, and hopefully this will like help clarify some confusions and show some more examples of things. And these will be sort of similar questions to the assignment questions. So if you don't come to the tutorial, I would recommend, like, for help with your assignment, to look at least the lecture notes or something, because they probably will help. Okay. And the assignment will be released tomorrow night. Cool. And also these lecture notes, they're going to be posted on the website. They are posted on the website. So someone asked that they wanted them posted before the actual lecture so they can like download them and annotate them and stuff. So now they're actually on the website before, so you can like do what you wish. I will mention though that this lecture today, there's like the last little bits are still not filled in, so they're going to be like added to for on Tuesday and stuff. So just so you know. Okay, cool. So let's get started. So I'm actually going to jump back to the math review very briefly. And there's two concepts I really wanted to go over before we get to actually using them, which is these partial derivatives and gradients. And these were typically introduced like later on when they start getting used, and they're not actually explained at any point. So I'm just going to briefly explain them. There's going to be a couple questions on the assignment and stuff, just getting familiar with doing derivatives with gradients and stuff, so that maybe when you get to it, you're a little less like confused and stuff like that. So it's just like one quick page of this. Okay, so here's the math review part we ended with. There was like this derivative chain rule business. What we're going to do now is take derivatives of, okay, so we're going to take these things called partial derivatives. And these are going to be, let me just see if there's anyone saying anything on the chat. Okay, cool. And these are just going to be derivatives of functions that can take in as input multiple variables. And this is probably going to be quite like intuitive why we would care about this, because as we talked about, there's going to be these like learners that take this giant tuple as input, and then there's this like predictor function which takes in also a big, like the features could be a large vector as input. So we're going to care about these kind of functions. And so some simple examples, which will be enough for, I guess, your understanding, will be, you can imagine now you have a function that takes in two inputs, which is like x1 and x2. And now you have to take the derivative with respect to each variable kind of independently. And the way this works is you think of the variable you want to take the derivative with respect to, and you write it like this. So it'd be like the derivative of your function with respect to the variable x1. And then you hold everything else constant. So that means you would think of like this x squared term as a constant. And so then when you take the derivative of this function with respect to x1, you just basically take the derivative of this term because you think of this as just a number. And the derivative of a number is 0. So the number you get here is 2. So that's the partial derivative of f with respect to x1. If you do it for x2, you think of x1 now as a constant, and you take the derivative of this term. The derivative of this would be 2 times 3 times x2, which is this term here. Okay. The type of things we're going to see in the course is like functions of a vector, which you can think once again of the vector as just this tuple. And so in general, we're going to have something like this, like a function of a vector. You're going to have something like more explicitly, it's written like this, which means it's a function of the variables. Okay, this is the function. I've just written some function. This is an example of a function I've defined that it could be. And this is one you're going to see a lot. This is called like a linear function, and it's actually exactly this dot product thing we saw before. And to get familiar, you can also write it using the summation notation. Okay, you're going to see this kind of notation, this like moving between these three kind of notations a lot. Okay, and so here's something really important to note. So it's going to be communicated sometimes that we think of some things as variables in the function and other things as like constants. And so here in this function, we're going to think of this x vector as the variable. So there's d variables. And we're going to explicitly say that this w thing is just a bunch of fixed numbers or constants. We're not going to think of it as a function of w. And the way to think about this is this is like a number. Just like here, you could think of this as w1 and w2. So we don't care about anything about how the function behaves with respect to those numbers. Okay, and this will be like explicitly pointed out that like this is the variable of the function, and the variable will always be like passed in, and then the other things in there will be like considered as constants and stuff. Okay. So now how would you take the derivative of this object? Well, just like before, you take the derivative of each individual variable one at a time, and that's how you get their partial derivatives. So the partial derivative of d of f, or sorry, the function f with respect to x1 is just look at the function, fix everything else, which means fix like everything after x1, and think of that as like a constant, and then take the derivative of the function. It turns out that this is w1 and so on, and every single one of them is just the w terms. It's just like yeah, okay. That's all I have to say about this. But the point is, you're going to see functions of this type a lot, these kind of like dot products, and then you're going to have you're going to have things more complicated, like for instance, maybe this will be squared, or there's going to be like a minus of y, let's say, and squared, and things like this. So then you have to use the chain rule and things like this. But the important thing is to understand how to deal with these like vector inputs. Okay. And then the last thing I just want to point out is there is this notion of a gradient, which really is just, you can think of it like it's really just a vector of all the partial derivatives listed like one by one from the first to the last one. So the gradient written like this of f is just like this vector. We're going to write it. It really is a vector, but you can write a vector is just going to be in this class represented as a tuple. So you can think of it as just like a tuple of each partial derivative listed one after another. Okay. So you just compute the partial derivatives like we have here, and then you list them comma separated in your tuple. And once again, the example from like if we take the previous example, the gradient of this function, which was this dot product function, is just equal to each partial derivative listed one by one in like a tuple like this, which explicitly when calculated is like w1 up to wd. So these things will be important. So there'll be some practice with this, and then we'll see it when we start actually learning functions. Okay, that's all I have to say about that. Cool. Now we go to probability world. And I briefly mentioned at the end of last class where this probability business even shows up. Why did we care about it at all? And it's because in supervised learning, we think of the data as being randomly sampled. And this is a standard way of thinking about it. Think of the data, and what's the data here? The data is like the data set. So we think the data set as being randomly sampled, like it was just gathered in some random way. And here it's going to be gathered in an even more special way, which is that each one of these feature label pairs is gathered kind of independently of the other. So like one classic example, which is not machine learning related, but of something similar would be like if you had a coin, right? You can think of a coin as just like a random flip of a coin. Well, then you can think of having like a tuple of n flips of a coin, right? So here each coin flip is kind of thought of as independent of another, and then you could imagine this is like n coin flips. Here they're not the outcome of the coin that we're looking at, they're actually like would be let's say the number of rooms and the price of a house. But it's basically going to be exactly the same way you can think of it. So this is what the random, and this is, and it has the special property that these things are going to be independently sampled. So each feature and label is independent of the other. And once again, that to like really exaggerate that point, that would mean something like when you pick one house, it wasn't influenced by any choice of houses in the past. Okay, and this is like a very important but standard assumption that's done in this supervised learning business. Okay, and the point of this class is going to be to basically understand what this means more precisely and like be able to deal with these objects and talk about their expected values and things like this. Okay, so if you're not familiar with like what's written here, don't be worried yet. This is just like to prime you with what things are going to be. Okay. And one other thing I've done is I've written D as just like a regular D, not this calligraphic D, and a capital D, because typically we're going to talk about random variables. And so here, this D is going to be called a random variable. And capital letters are usually used for random variables. Okay. And then one more thing we'll see is that you saw this kind of notation, and this just means, this kind of thing means like sampled according to this distribution. All right, that's all I wanted to mention about the background. Now we go into the technical details. So here is what the agenda is going to look like. Okay, so probabilities, like the topic we're going to go over. It's going to be kind of like just what's needed in probability theory to do the course, I hope. I tried to make it just that, but maybe I went a little over the top. We're going to find out. And here's my little inspiration for probability, or a note. There's this book called like Thinking Fast and Slow. Some of you might have heard of it, and somewhat of a common theme in it is this idea that like humans have really bad intuitions when it comes to randomness. And this means like their first kind of instincts towards like, should I bet on this or should I do this thing? It's like usually like mathematically, like if you try to compute the probabilities, is quite a lot of time quite incorrect. And there's like all these different biases that we have. And if you read the book, you'll see this. And the book's by Daniel Kahneman. But I just wanted to mention this because you might think that probability is like the super easy, intuitive thing. Like you just flip some coins and everything's like 1/2 probability or something. But it turns out that when you start asking like more nuanced questions and stuff, it does become like quite unintuitive sometimes. And it is important to actually work things out like in this like, I guess, formal mathematical way to get correct results. And maybe we'll see some sort of, I don't know, unintuitive things in this class. I don't know. We'll see, but just keep that in mind. This is important. Okay. And this is the agenda of the class where this is like usually what you see in a probability course. And we're just going to kind of review it at a high level. So there's these notions. We're going to talk about these notions of random variables. Then we're going to calculate like the probabilities of some random variables using these things called PMFs and PDFs. Once again, everything's going to be defined. And then we're going to introduce this idea of a multivariate random variable. So just once again, to foreshadow what's coming is like that data set is going to be a multivariate random variable. You can see it has like multiple variables kind of inside of it. Okay. And then there's going to be, when you have multivariate random variables, there's going to be notions of a conditional probability and a marginal, and there's going to be, yeah, things like this. Oh, this thing is not going to be a subset of that. Okay, let me fix this. This is not the order this is actually going to be presented. So these things are actually written up, and these last two are not written up yet, just for reference. Cool. Okay, this is the order. Then, like this little section here is us actually going to be, I'm going to actually show what how using all this notation we can represent the data set and features and labels as random variables and stuff like this. So then that should be a really nice point to like understand what that looks like, and then we'll cover these functions of random variables and expectations. Okay, let's begin. So I'm going to start with a wonderful warning. And this is a warning that's not maybe typical in a probability course, but I'm going to say it because I was a little annoyed of this when I took probability for the first time. And it's that you might find some or many things in this class informal or imprecise or confusing. And some of the time, it's actually warranted, and it's like good that you find these things because there's going to be things that are like presented informally actually. And the reason for this is that to present them formally, you're going to need tools from this field called measure theory, which you probably or maybe have never heard of. It's basically the like math field that all of probability is actually built on that you never hear about or see. And so, which we won't cover in this course, so that stuff is going to stay confusing, but I will try to point out in the few places where things are just going to kind of be a little hand wavy, and if you want more details, you really, unfortunately, like, if you want things precise, you should know measure theory. But once again, for this course, you don't need to know any of this. It's just for people that are curious or get confused with things, like, there's a reason. So yeah. Okay, let us begin. So probability is usually motivated by this, or like, actually not even motivated, it's like kind of at the heart of it is this idea of an experiment. Okay, and an experiment is just like some process that generates uncertain outcomes. That's what we're going to think about it. And some examples are like you flip a coin, that's an experiment. Or you roll a dice, that's another experiment. Or in our course, it's going to be like you pick a house randomly, and then you observe its number of rooms and things like this. These are going to be your experiments. Okay, and then your experiment has an outcome, right? That's what I call it. So there's going to be this thing called your outcome space or your outcome set. This is just the value that your outcomes can take from your experiment. And for this course, our outcomes are always going to be numbers, and we'll kind of cover this in a second, but keep that in mind why I've used numbers everywhere. So here, this would be like your outcome space Y, okay? And in this case, it would be, there's two outcomes when you flip a coin. And the first one, we can use 0 to represent tails and 1 to represent heads. So this would be like your outcome space. And I'm kind of emphasizing this because this outcome space is going to be important throughout. You need to know like what is the set of possible outcomes. So for rolling dice, a typical outcome space you'd write is the numbers that the dice could represent. So there's numbers 1 to 6 that the dice can have. So in the case of like trying to classify wine that we saw in the first lecture, there was this notion of the amount of a chemical. And here you might use the interval 0 to 900 to represent the outcome space. So you could have the amount of a chemical could be any value, let's say between 0 and 900 milligrams. And then like maybe some classic example of something that's actually a real number that can go like potentially as large or positive or negative is like this idea of measurement error. So like when you measure something, it could be like plus some amount minus, and maybe you don't have any range on it or something. But anyways, this is going to be the set of outcomes that your experiment can take. And then here is where the countably and uncountably infinite thing comes up, because we're going to have to distinguish between this notion of discrete and continuous outcome spaces. And why do we do this? Because there's going to be these things called discrete and continuous random variables, which are related to this. Okay, and maybe just a note, it's like if you do measure theory, you don't actually ever care about these kind of different things. This is, once again, done in real, like in these type of probability courses to like make it simpler, and you handle things separately in these cases. But for this course, we're going to do things separately as continuous and discrete, which you would see all the time anyways. Okay, so examples of discrete random variables. It just means that the set of outcomes is finite or countably infinite. So examples are going to be like this y or this x you saw, and I'm going to write it many times, so just kind of remember x is the rolling a dice, y is the outcomes for flipping a coin. And another important one to know is the natural numbers is also called a discrete outcome space because it's countably infinite. And then uncountably infinite, you're going to see things which are like intervals or the real numbers. This is basically all you're going to see. So like the intervals 0 to 900 or the reals. Cool. Okay, after you have these outcomes, there's going to be a notion of an event. So we're going to go over a bunch of different events. And so for the purpose of this class, we're going to think of an event as just any subset of the outcome space. And here I'm pointing out that this is imprecise because it actually is a special, like an event is not just any subset of an outcome space. It has other special properties, which once again, we won't talk about. And in this class, you can just think of it as a subset of the outcome space. And that'll be enough. And so like, what would an event be? Well, here's some examples. So if we have the outcome space of flipping a coin, an example of an event is getting a tail, which is represented by the number 0, or getting heads, which is represented by the number 1. And here is where it gets more interesting, is your events can have like more than one thing in the set. So this is the event of getting heads or tails. Okay? And this is the event of getting nothing. And that's always going to be an event that's there. Probably not even going to need to know that in the course, but that's the empty set. It's the event of getting nothing. Okay. Here's a more interesting one, maybe, is if you have the outcome space of rolling a dice, so you have the numbers 1 to 6, then the events would be things like rolling the numbers 1, 3, and 5, which is like rolling an odd number, or the event of rolling an even number, right? And this is the event of rolling a number less than 3. So we're building up to it. We're going to want to know like what's the probability of these kind of events. That's why we're introducing events. Okay, and similarly for the wine thing, you could have like the probability of getting a wine that has 0 to 4 milligrams of some chemical, or 1 to 2 milligrams, or 7 to 30. This is where the union thing kind of comes in. But okay, events just subsets of outcome space. Okay, so now we're getting to the actual part of probability, which is we're going to talk about probabilities over these events. And these probabilities are going to be called probability distributions or just distributions. And this should hopefully be like the familiar word you've heard before. You've heard of maybe normal distribution, or like a Bernoulli distribution, or uniform distribution. This is what they all mean. And the way we're going to think about a probability distribution is like in words is going to be it's defining the likelihood or maybe the probability of some event. And it's very important, the word event, because you're going to like, why is this important? Well, this probability distribution, right, it's going to be a function. It's going to take in as input an event. And it's going to output some number between 0 and 1. Using our function notation that we've seen in the math review stuff, the way you would write a function, right, is you write here the set of all possible inputs and the set of all possible outputs. That's the code. And so this set of inputs is going to be the set of events. And this thing is typically called this like event space. Okay? And so for the purposes of this course, we're just going to think of this as the set containing all the events, and events are going to be subsets of the outcome space. Okay. And here's another note. So there's not going to be too many more of these notes after this. Like, it's just the beginning. I'm going to point these things out, and then after, we're just going to work with what I said. So this red note is, once again, the measure theory note, which is that we're not actually going to keep writing this function in this way and keep writing in words, event space, and stuff. It's just going to be assumed that when I write this thing, the probability distribution that looks like this, it takes as input events, okay? And the reason I only wrote this thing in words, this event space thing, is because this thing is actually a more complicated set that needs to satisfy like special properties. It's this thing called a sigma algebra in measure theory. Once again, you're not going to need to know it. We're not going to define it. But if you get curious why, this is why. And in the notes, there's actually going to be like a thing in the appendix that goes over it that Martha wrote at some point. So if you're really curious, you can see these things. Yeah, there's a question.
Sorry, is the power set?
Yeah, so the question is the event space just the power set of the outcome space? And the answer is, it can be, and that is a valid event space if your outcome space is discrete, okay? You can have event spaces that are smaller than that, and that's also valid. And it turns out that it's sometimes important to talk about these different things. In this course, we're basically going to just think of it as the power set all the time. And another nuance why measure theory kind of becomes important is if you have this continuous outcome space, and this is not to confuse people, is there you can't use the power set anymore. And what I mean by you can't use is that you wouldn't even be able to define the notion of a uniform distribution on a continuous interval if you cared about events on the power set. But it turns out that you can almost use the power set everywhere, which means you can almost talk about events that are subsets of the outcome space everywhere, and you're almost never going to write an event that you can't talk about its probability in such like a course like this, so you never need to worry about it. But it's possible, and maybe just I can say like one word, which is there's like examples of such events called like a Vitali set, if you ever want to Google it. And it's a very complicated looking set, which is an event is a set, and that thing has these problems and stuff. But anyways, just like math fun. So the purpose of this course, once again, think of this thing as taking input subset of outcome space, which is event. Okay. Yeah, another question. So from my understanding, the question was, is this thing a function? Is P a function? Is that correct? Yeah, so it is a function, and we're going to think of the function, right? How do you write a function? Just like, so for the things I mark up on during the class, I'm going to use green from now on. Like if I were to write a function like this, usually what I would write is, this is a function that maps from a set, let's say set X, to another set. Okay, let me write a clear set, which is like the set of all real numbers, to another set, which is a set of all real numbers. And that's exactly what I've written here. This is a set. So it's taking as input anything in the set, and it's mapping to anything in this other set, which is a number between 0 and 1. So yes, hopefully that makes it more clear. It's exactly a function. But we're not gonna write this type of thing. We're just gonna like always assume it's this kind of function, and we're just gonna pass things into it and things like that. Cool. Okay, and it turns out that this probability distribution has some special properties, which you probably already know and is very intuitive, but I'm just gonna write them out. And these are also stated slightly imprecisely because you need kind of like sigma algebras and stuff places, but this is all you need to know for this course. So here is, so you have some outcome space, let's call it Z. Then this is basically these are the two properties your distribution should satisfy, which is that the probability of the entire outcome space. So like for rolling a dice, this would be the probability that you get the number 1, 2, 3, 4, 5, or 6. Should be 1. Like you ought to get something that's in your outcome space if you're going to like do the experiment. The second thing is if you have two events, and so here these are going to be denoted as events. They're just subsets, right, of the outcome space. And visually you can see it like this. So this is the whole outcome space. And so you have just two events. And they have the special property of being disjoint. And this word disjoint just means that their intersection is 0. As you can see in the picture, they don't share any outcomes between each other. And if this is the case, then it so happens that you can write the probability of the union of the two events, right? So this would be like the probability maybe of getting, let's say, a 1 on the dice, and the probability of getting a 3 on the dice, or getting a 3, would be equal to the probability of 1 plus the probability of the other. This is going to be, yeah, you're going to see this. And like an immediate consequence of this rule, and you can, immediate consequence of this is that suppose you had the two events, which is like some event, and then you had the complement of it. Notice that these two share no common outcomes. Then what you can do is you can just use this exact property to write something like this. And you notice that this event with this event is the whole space of outcomes. So that probability is 1. And so you get probably this other common result that you've seen a lot, which is that the probability of some event is equal to 1 minus the probability of its complement, which would be like the probability of getting a 1 on the dice is equal to 1 minus the probability of getting any number other than 1 on the dice. And this is going to be an important property that gets used a lot too. Okay, great. So here is some examples visually of what this like probability distribution might look like. So if you have some outcome space like the heads or tails example, then you have to define this probability distribution function for every event. So there's only 4 events, luckily, for this small outcome space. And those 4 events are like getting nothing, getting a tails, getting a heads, or getting a heads and a tails, which is just the whole outcome space. And visually, like here's a fair coin. The probability of like any one of the heads or tails is 1/2, while getting either of them is going to be 1. This should be intuitive. Okay, here's a slightly more interesting one, which is if you try to write this probability distribution now for all the events for the case of rolling a dice, you already start running into this case like this problem where there's a lot of events. And if you want to define this function, you have to define its value on every event. Okay, so here we're going to see like, let's first do these single events. So it's like the event of getting a 1 or a 2. And notice how I'm passing in sets here for now. So here this is a fair dice, so the probability of getting any one of these is 1/6. That's denoted here in this picture. But then you need to list like every other thing. It turns out because of this like disjoint property, you'll be able to, in this case, to decompose them in this way, which is like the probability of getting a 1 or a 3 or a 5 is just each of the probabilities summed together. And so you can already see that there's going to be some like inclination to be able to not just have to write this distribution in this way, but use something to help us with it. And we're going to see this in a second. And it's going to be basically doing exactly this type of process to define distribution. And once again, this is to highlight that like there's a lot of events here that's missing. And if you want to define the function, you should define what it does on all those events as well. Okay. So for that, we're going to end up introducing these things called like PMFs and PDFs. We'll get to that in a second. But before that, there's also this notion of probability that you probably hear a lot. It's called a random variable. And this can get very confusing. But once again, we'll try to like just make it simple-ish for this course. So for this course, this random variable, you're going to think of it as just a variable. Okay? And it's a variable that's going to take values in the outcome space. So you can kind of think of it like just an element of the outcome space. And it takes values based on an experiment. So like this experiment, you roll this dice, it gives you some random thing, and you're going to think of that outcome as your that value of the outcome as the random variable's value. And each of these random variables is going to have like this associated probability distribution, which means like this thing tells you how the randomness from the variable was kind of generated. And that's going to be the high level understanding we have of random variables in this course, basically. You're going to think of it as something that's an element of the outcome space. This like the values it can take is just some outcome. And the probability that it takes any of these values is going to be based on some distribution. And that's all you're going to really need to think about it as. And you might be a little unsatisfied with, okay, and there's one more very important property, which is that we're always going to use these values as real numbers. So they're going to have to always be, like they're going to be numbers. They're not going to be something like, for instance, you wouldn't write heads or tails. Sometimes people do write it like this, but for this course, we're always going to use it as real numbers. And it will make everything else much easier. Everything's going to be a real number. You can add them together. You'll be able to take their average and things like that. And yeah, okay. And in red, I'm going to highlight like the more kind of precise story of these random variables. So it turns out that this random variable is actually not a variable, and it's just a function. But once again, so you're not going to need to know any of this for this course. But it's actually a function that satisfies like some special properties. But the high level story is that it's going to be this, like, it's usually thought of as this function that maps from one outcome space to another. And it's precisely like this case of like, what you actually observe is not like a like when you observe a dice roll, you observe like the dice being rolled, which is like maybe a visual scene of the dice, and you interpret this one looking thing on a dice as a one. And so the formal definition of random variable is actually going to be like a function from this underlying outcome space, which is the thing you actually see, usually in an experiment, and mapping that to some number. And that's like the actual story behind where these things came from. But yeah, for this course, you're going to like always implicitly do this mapping right away, which means you're going to define outcome spaces as always real numbers. Then you're going to say like, oh, this number kind of represents the number 1 on the dice, or this represents the tails of a coin. And then your random variables are just going to be elements of it, and that's it. No functions, nothing like that. Yeah. Sorry, where is that written? Here? Yeah, so like this is just kind of like a property that a distribution has. And so once again, an event is any subset of the outcome space. So the outcome space itself is an event, right? Because the outcome space is a subset of itself. It's exactly the whole set. So you can talk about that event. That's the first important thing. And the second thing is like, this is just like a way we define the distribution. And exactly we define it in this way such that it satisfies this intuitive property which we would want it to have, which is the property that the probability of getting any outcome, which would be like the event, which is the outcome space, that kind of represents the probability of getting any outcome, should be 1, meaning that you are certain to get one of those outcomes. So this is just a definition, or like you have a distribution, and it's really defined this way to satisfy this intuitive understanding we have of probabilities. So there's a question online which is saying, how can we train the data out of the sample space? I don't really understand what the question is asking, but the story is going, like if it's asking how the training data or the data set is related to the sample space, well, the sample space, the sample space for the machine learning thing and the data set world, as I said, the sample space is, sorry, not the sample, like the outcome space. Sometimes it's called sample space. Hopefully I say outcome space to be consistent in this course. The outcome space is some set of objects. And that set of objects, I'm just going to briefly write, for the data set case is going to be this like complicated thing like this. And this is a set, right? This is a set of these tuples like this. But this is just a set. And this is actually going to be exactly our outcome space for the machine learning case, which is going to be like, you can get any data set, right? This is the set of all data sets, the set of all tuples of length n. And you can get any one of them. And certain one of them maybe are more likely than others, meaning like getting certain house prices is more likely than others. And that's going to have a corresponding probability. So maybe just, I don't know if that's the question, but that's like kind of foreshadowing why this is at all important and how it's related at all. This is going to be really the outcome space we're going to be working with for the data sets. Okay, let us move on to these random variables. Cool. And so, okay, so this is the usual way you've probably seen probability distributions written with random variables, and the way we're going to write throughout. And it's okay. There's like the deeper meaning of why it's written like this, and then there's maybe the simplified meaning, which we're going to talk about again in this course, which is that the simplified meaning is it's way more kind of like English interpretable. And so this probability distribution we wrote as like, it takes in as input an event. Usually this is written as the random variable is an element of this event. And the way to think about this is like when you do some experiment, you get one outcome, right? But then you ask, what's the probability that this outcome, which is like the random variable, this is the random outcome, right? What is the probability that random outcome is an element of some set? Or like, what is the probability that this random variable, like that maybe the roll of a dice, what is the probability that it's a 1, a 3, or a 5? So that's how it's going to be written. This is going to be interpreted exactly as the same thing as this. This is like, I suppose I should write like something like, this is the definition. These are equivalent. The reason why this is kind of weird is because like this is not like an event. This is like some weird looking math notation, but it's an equivalent math notation. And then you're going to see some other really like confusing notation, but I really want to highlight these are all the same thing, which is you might see something like, this is what we were so far comfortable with, which is like I plug in an event. This is like me getting the number 4, 5, or 6, a number greater than 4, intuitively, right? You could write it using this random variable notation, which is that my random variable is a 4, a 5, or a 6. Or what actually ends up being written is this kind of notation that my random variable is greater than 4. And this is just shorthand to interpret exactly this, which is that your random variable is in this event, which is itself just this thing. Okay, so you're going to see this kind of notation. And one more other kind of notation you'll see is that when there's a single event, like when your event is just a single outcome, then instead of writing something like your random variable is inside this set, which is a single outcome, people will write that the random variable equals to that outcome. And once again, you should always map it to this more like kind of precise thing, which is that it's actually, this means that your random variable is in the set, which contains just the number 4. And this is your random variable is in a set that contains all the numbers greater than 4. Okay. And this is just really important to drive the point home that this P, this distribution with this like double bar here, is taking in as inputs events. And this is going to be in contrast to these PMFs and PDFs we're going to see in a second. Okay, and one more notational thing, which is when you write something like this, which is that a random variable, and then you write this like squiggly thing, this is read as the random variable Z is sampled according to that distribution. So it's like I roll the dice according to the distribution, which has a uniform probability, the same probability for every number on the dice. And we already saw this for the data set example at the very beginning, which is I wrote this squiggly thing and said the data set is sampled according to some distribution over data sets. Okay. So now there's going to be 2 types of random variables we're going to talk about, and there's going to be discrete random variables and continuous ones. And once again, this countably and uncountably infinite thing becomes important, which is so. The definition we're going to use for this course is that a random variable that's discrete is just a random variable that has corresponding outcome space that is discrete. And this is the usual definition you'll see. Discrete random variable means discrete outcome space. We're going to add one more minor note that isn't usually like usually mentioned, but it's actually equivalent, which is that or you can have, so or all the probability, okay, is only going to be situated on a countably infinite number of the outcomes, not an uncountably infinite number. Okay, so let's just go through an example of what this means. So, and this will be important to the like our case, because remember we said like the features might be like actually just natural numbers, like number of rooms. It might be 0, 1, or 2, or 3. But we're going to think of them as vectors, which are elements of the real numbers. But that's like an uncountably infinite thing. But really, the probability only, you can only get like the numbers 0, 1, or 2, or 3 rooms. So this is where this relates to, and we'll see it in a second here. So this is the usual way you think of a discrete random variable. It's just a random variable that belongs to an outcome space where the outcome space is discrete. So this is discrete, it's finite. Another discrete outcome space is this, it's a finite one. Here's another one, this one's countably infinite. Okay. The second example is highlighting the other case, which is that all the probability is only on a countably infinite number of outcomes. Okay. And so the idea is that you could take this outcome space, and if it had, like, think of this as the, so the thing I didn't include here is obviously the probability, like with respect to the random variable as well. But you can imagine for this like dice rolling case, you think of the probabilities of each like number being 1/6. So that's exactly the following, right? So the probability for this outcome space is going to be 1/6. Okay. And so here, what I'm claiming is that you can extend this outcome space to basically all the real numbers. So that means take this outcome space, extend it to the real numbers, but keep the probability at these discrete number of outcomes as 1/6. Okay, and so you can always do this, and like maybe pictorially this makes a lot more sense, which is that all I'm doing is instead of saying my outcome space is just these 6 numbers, I'm now saying my outcome space is all the reals. Okay, but all the probability that sums to 1 is on only a discrete number of outcomes, which is exactly these 6 outcomes. So what that means is that the probability of a discrete number of things, which is just these 6 things, is 1, while the probability of the real numbers minus this discrete number of 6 things, which would be like this line and this thing, all these like this remaining thing, which is like a lot of the space, is 0, right? So we just set that to 0. So you could always, the takeaway is you can always take a discrete like outcome space, which you have some probability defined on, and extend it to a real, like an uncountably infinite outcome space. And so we're going to do this all the time. Like this just gets done implicitly in machine learning all the time, which is that you take some features, which are usually like some discrete description of something, and then you talk about them as vectors, which are real numbers. But really, you always talk about the distribution as if they're discrete, but then you work with them as if they're uncountable, like as if they're on this real number line. And so that's why I put this here, because this could be confusing. A lot of the time, like you might think like, what is the point of these discrete distributions? You're always dealing with vectors, which are real numbers in machine learning. But this is the story. You end up like thinking of their distributions in this way over the discrete space, but then you just extend them to the real numbers in this way. Okay. I'm going to answer the question on the chat right after I introduce the continuous one. Okay, so, and this is the node basically saying exactly what I said, which is that you can always take a random variable defined on a discrete space, and you can define it on a larger continuous space. And you probably won't actually need to like formally do this very much at all in this course, but you should like just know this information. Okay. And so the continuous random variable is just like kind of the opposite of the discrete one, which is that it's a random variable that takes values from a continuous outcome space. And here's this like really weird property, which just bear with me for a couple pages and I'll try to make it sort of intuitive, which is that it has, so its outcome space is continuous, but it has this really weird property, right? Which is that the probability of any single value, which is like any single outcome, is 0. Okay, so what would that look like? This is going to be really weird. So you might have a random variable on the interval 0 to 900, which is like 0 to 900 milligrams, let's say, of some chemical. A continuous random variable would be one for which the probability of any single value being 0. The probability of any single value is 0. And this is the value of all these. Any single value. And here you might be very confused because I told you that the probability of this random variable being the entire outcome space, so like an element of the outcome space, has to be 1. So this property is satisfied. But somehow every single value is 0. And usually this is just like kind of put to the side, and that's kind of what we're going to do too. But the short story, like the thing you might think like, wait, can't I just create this set by taking the union of all of these numbers and then get that, and then this thing, I can just add them up and they're all 0, and then how did I get 0 from 1? Like what is, and the story is going to be that we didn't do things formally before, and what happens is that you might remember I had this whole property I talked to you about, which was that if you take the union of two things, you can write it as the sum. So you might think, okay, I'll just write it as the sum, and then this thing's 0, and then this thing's 0, and then just the sum of zeros, how do I get 1? Well, it turns out this property actually only holds for this notion of countably many unions. And this interval is uncountable, and so here math, you get some, there's some details and things don't work because this property only holds if things are for countable unions. But the interval, you can never make an interval from 0 to 900 with uncountably many unions. And so then things don't break. But once again, for this course, you don't need to know this. I'm just pointing this out because when you see something like this, you might initially think like, what the heck? Like, how does this make any sense? And it does, but yeah, we're just gonna trust it and believe it, and that's what it is. Okay, and similarly, if your like random variables on the real line, which means any real number, then once again, it's continuous if this probability is 0. But of course, the probability of the whole like event, like the random variable being any real number, is 1. Okay, and I'm hoping that in a couple pages, this is going to become much more intuitive through an example. And yeah. Okay, and notice how here in the discrete case, even though I made the outcome space continuous, like the real numbers, it didn't satisfy the property where the probability of any single value is 0. Here, the probability of 6, there's exactly 6 values. They had non-zero value, which is 1/6. And so this thing we call discrete, because it did not satisfy the property that the probability of every single value is 0. It might seem weird, but that is what it is. Okay. So next we're going to talk about this calculating probabilities, but before that, I will answer some questions on the chat, which is that, I mean, it's about the training thing again that I responded to earlier, which is that, I mean, if I want to train beyond my data, let's imagine if there is a dice with n or infinitely many sides, or let's say if there is a different property of the data in the whole world going to infinity, how do we train on those? And also, is it possible to train the model without actually having much data to answer the given inquiry? Okay, I think I'm a bit confused. I'm gonna just say, maybe ask this on Piazza's to save time. And yeah. And then the second question was, in our machine learning model is trained on super fast hardware, let's say quantum computers, how would the model react to it in solving highly complicated tasks? Yeah, maybe if you can, just please ask this on Piazza or like come to my office hours or something, because I don't quite understand and I don't want to waste more time in the class. Okay. Sorry about that. Okay, so we move on to calculating probabilities. And by probabilities, I mean calculating the values of these probability distributions on an event. And this is all kind of motivated because I said, okay, there's a lot of these events, right? These events are any subset of the outcome space. Imagine trying to write this function for every single value for every event. It's going to be hard. So the way we get around this is by defining something called a PDF and a PMF. And these are probability mass function, and then we're going to see probability density function later. And the motivation, yeah, it's exactly what I said. It's hard to define this distribution for all the events. So what turns out, we only need to define it on the events, which are exactly the events that contain single outcomes for the discrete case. And that's what this probability mass function does. So notice how this thing is now going to be denoted by a little p without the double bar. And it takes as input elements of the outcome space, right? It does not take in inputs events. So it just takes in elements of the outcome space. And here's the definition you need to know. So probability mass functions, first of all, they're for discrete outcome spaces. And so for discrete random variables. And so here is the definition. The probability, like the probability distribution of like a random variable being an element of some event, is equal to the sum of this PMF, little p, for every element in that event. And let's just go to an example, and you'll see what this slide, like what this means. And it's basically what we kind of saw already, which is that let's imagine we have this outcome space Y, which is this flipping a coin, and you get heads or tails. So the PMF for a fair coin would be something like this, which is that the probability of getting tails is 1/2, and the probability of getting heads is 1/2. And notice how here I just put in a number. That's the outcome. I don't need to put a set. I don't need to put the random variable as in some set, which is like the event. I just put a number. So, yeah. And now I can use this thing through this definition here to give me the value of the distribution for any event. And this is how you would do it. You would say the probability that my random variable is an element of some event is just by the definition equal to the sum of the PMF at every single element in that event. So here the event is 0, 1. So what I do is I take my PMF, and inside I plug in 1 by 1 every element of that event. So this would be read as the probability of like the probability of my random variable being in this event of getting a heads or a tails is just equal to the sum of these things. Okay. So these PMFs are going to let us compute any basically probability distribute, like the event of any for any probability distribution. And another example is like if you just had this case, and this one's kind of like the obvious one, which is that if you ask what is the probability that my random variable is equal to some number, which should be interpreted as what is the probability that my random variable is in the event that contains just the one number, well then it's exactly equal to just this PMF for that one number, right? Because the sum is over one element. That's 1/2. Okay. And so visually you can always write the PMF. It's like very easy to write because you just write the probability for each outcome. And so like your outcome space, you can just write each one by one if something's discrete. Okay, and for the case of rolling a dice, here you can, without even looking at the math, you can kind of imagine the PMF once again tells you the probability of any single outcome. And if it's a fair dice, the probability of each of these 6 outcomes is exactly 1/6. So this is how you would draw or like plot the PMF. Okay, it turns out there's some common PMFs that are used like everywhere. And the two that we're going to need to know for this class are going to be these. They have a name. They're called, the first one is called a Bernoulli distribution. And a Bernoulli distribution is just a little bit more general than the like flipping of a coin. So here's what it is. The outcome space is, once again, just like we saw, 0 and 1. And the PMF is a little bit more general in the case that it's not 1/2 of getting each one of these outcomes. It has a variable, which is called alpha, or sometimes called a parameter. It has this parameter alpha, and that tells you the probability of getting 1. And then obviously 1 minus alpha is the probability of getting 0. So this is like flipping in a biased or an unfair coin. So the chance that you get heads is alpha, while the chance that you get tails is 1 minus alpha. And so the plot is, yeah, this is the plot of it. That should make some intuitive sense, I hope. And to be precise, it's written like this: Bernoulli of alpha. So it's a Bernoulli random variable with parameter alpha. And in particular, it's the distribution is a Bernoulli. Okay. And once again, like a lot of the time, you're not going to work with distributions. You're just going to define PMFs. Like all you need is the PMF. Once you know the PMF, you then always get the distribution through this property. So this is going to be really important. Like all the things that are in the purple boxes are going to be like the important things that you're going to actually end up using to solve problems. And so this is important. Just if you know the PMF, you can compute the distributions. That's what you need to know. Another important PMF is this discrete uniform distribution. Okay, there's going to be a continuous uniform. This is the discrete version. And so the discrete uniform distribution is just, so it has this like parameter n, which just says this is the number of outcomes. You always write the outcomes as like 1, 2, up to n. And the uniform part just means that the probability of each one of these is split evenly. So if you have n of them, the probability of each one is 1 over n. In the case of rolling the dice, we had 6 of them. That was a uniform distribution where the probability of each dice roll was 1 over 6. And so this is like kind of the generalization of the dice roll, while the Bernoulli was the generalization of the fair heads or tails flip. And so once again, when we write something like uniform n, we mean that the distribution p, so this thing p, is uniform, which obviously has this corresponding PMF. Okay. So this is for the discrete cases, right? Like I said, there's this PMF. The PMF just tells you the probability at every single point. But there's only a discrete number of points, so I can just tell you, list all the probabilities one by one. Okay, so you run into problems when you try to do this for continuous outcome spaces. Why? Well, just I'm going to do it with an example and stuff, but like the high level thing is like, imagine like if you had the interval from 0 to 1 or 0 to 900 or whatever, imagine trying to write the probability of every single number. Well, that turns out to be like, unless you only write it for a discrete number of them, you can't actually write it for all of the infinitely many. And okay, so here's the intuition. And I tried to do this with like maybe something that you're more familiar with, which is this example of a rod or like a stick or something. Like you can think of this pencil in physics. And so this is how this notion comes up. And even the like naming, I would claim, is partly coming from physics. So notice, so this left-hand side is kind of what we've seen already, which is this idea of a probability mass function. And you can think of this as describing like the mass of some object. So at the bottom, we think of a rod. And here we're going to think of a rod that has no weight anywhere. So you can think of it's like a 0 mass rod everywhere except for at the endpoint. So these black things denote that this is the only place that has mass. Okay. So then to describe like the mass of this rod, all you need is the mass at this discrete number of points. In this case, it only has mass at 2 points. And so you can think of this like probability mass function as kind of describing the mass of this rod at these 2 points. So it would have a mass of 1/2 here and a 1/2 here. And this probability mass function has this critical property that the mass always needs to be 1. So your rod always needs to sum to 1. And so here, hopefully, is the intuition for why you should think of the probability at any single point to be 0. Okay. So when we move to continuous things, so here's the thing we haven't covered yet, which is going to be these ideas of probability density functions. Okay, so I'm going to motivate this by an actual rod like you would see in real life, like, for instance, this pencil. You would think of the mass like being distributed, let's say, like, in this case, like, let's say uniformly across the pencil. But there's not like a point mass here and a point mass here. It's really like every time you look at any individual point, it would be very, very hard to explain how much mass is at that point. To the point where like any point is like infinitesimally small and technically has zero mass. And this is how it's like thought of in physics. So if I look at any point in the rod, it has zero mass. But the way to get the mass of some part of the rod is to talk about that interval. Okay, so I need to talk about the interval. And in particular, what you would do is you don't define the mass at any point. You define the density, which is like how much mass is there per unit area. Okay, and so then you have, for continuous things, you have this notion of density. Okay. And so this would mean something like, if I want to know the amount of mass, let's say in this interval. Okay, well, if I know the density is 1, meaning I have like 1 kilogram per unit length, and this thing has length 0.5, right? This is 0 to 0.5. Well, then what I would do is I would multiply the length by the density, and then I get the corresponding mass. So here it'd be 0.5 times 1, and I get the corresponding mass of 1.5. And so instead of using this, like, you're not going to be summing. Okay, so like, let's see visually in this plot. So here's the density. This would actually be like a PDF. And then you say, okay, how much mass do I have between 0 and 5? And for the probability case, it's going to be like, what is the probability of getting something between 0 and 5? A number between 0 and 5. The way you're going to calculate this is you're going to take the density, which is kind of like how much probability do I have over a certain region? And then you just multiply it by the region, roughly speaking. I said multiply. We're going to fix this in a second. So that would be like take 0 to 0.5 and then multiply it by the density. And then you get 0.5 times 1, which is exactly this area here. So you think of the area underneath here as the probability. Okay. So here I've drawn this like nice, beautiful, smooth function. It's not always going to be smooth like this. And you're not just going to just multiply the density by the area or like the interval. What you're actually going to do is use integrals for this. And the integrals are exactly this. If you remember integrals, right, they would give you something like, if you had a more complicated function, it would be like the area under this more complicated thing. So that's how integrals come up. They're going to help you calculate things for continuous intervals. And so this is going to be the high-level motivation we have for why probabilities over continuous spaces are 0 at any point, but over like a region can be some actual number. Okay. There is a question on the chat before I define this. If the n is the number of outcomes in the uniform distribution, what does the alpha represent in the Bernoulli distribution? So regarding that question, so in the Bernoulli distribution, yeah, these represent slightly different things, which is in the Bernoulli thing, the alpha is not talking about the outcome space. It's talking about the probability of getting 1 in that outcome space. And the outcome space is, for Bernoulli, is always fixed to be 0, 1. It's always 0 and 1. And alpha just represents the probability of getting 1. In the uniform distribution, n actually does, well, it also describes the probability, but the outcome space is not fixed. So if you change n, this parameter n, then the outcome space changes. It becomes 1, 2, up to n. And then the corresponding distribution, or sorry, like distribution once again is defined by the PMF, but the PMF is also governed by this parameter n. And it's exactly 1 over n to have it uniformly over everything. Okay. Hopefully that answers that. And then someone asked, I don't understand the intuition of the rod in physics concept. I don't want to spend too much longer, but the story is that like you think of a rod kind of being made up of like infinitely many things. And if you look at the mass of any individual point, it's 0 because it's like infinitesimally small. And then if you want to calculate the mass of an actual region, what you do is you technically take like the mass of like an infinite number of infinitesimal things. Even if you want to like get the mass of something like at point x, and x plus epsilon, and epsilon is like tiny, tiny, tiny. That region still has an uncountably infinite number of points. So yeah, this is like the usual kind of story between how you go from summation to integration in calculus. This comes up in many places, and unfortunately, this is all the intuition I'm going to give until like formally deal with these things. We're not going to do that. We're just going to do this kind of like, this is enough. This is like these tools, like what I'm giving you is the tools to compute things and calculate things, but all the like background story you can't get, I guess, in these 2 classes that we're going to have for probability. Okay. So then we move on to probability density functions now, this is just going to be our shortcut kind of Just like a PMF was the shortcut to calculate the distribution for discrete random variables, this is going to be like our shortcut or like function that we use to compute the distribution of continuous random variables, which means that they have a continuous outcome space. This PDF also has this property similar to the PMF where its integral is 1. In this rod example, that would mean that this mass is still 1. So, or like it would mean this area actually under this curve is 1. Okay. And so here's the formula you're going to need to know, which is that it's almost the formula you saw before. Instead of summing up over all the elements of the event, you're now going to integrate over the event, and you're going to use the PDF here. You saw a sum before, now it's an integral. That's all I'm going to say. And once again, it has this property too, which is, whoops, I forgot. So very important to distinguish between distributions and these PDF or PMFs, because here, the distribution is 0 everywhere, but the density is not 0, right? The density tells you how much mass you have per some region. So these are very different things. Okay, and so now there's, once again, some examples of typically seen continuous random variables. And I'm sure some of these you've heard of before, which is, we're going to see the Gaussian second, but the first one is going to be this uniform version. And the uniform one, there's a continuous version, and there's a discrete version. We've already seen the discrete. The continuous is also kind of as you would expect. It has 2 parameters now, which governs the outcome space. It just is, the first parameter is the start of the interval, the second parameter is the end of the interval. They also govern the PDF in the sense that the PDF is just 1 over the difference between these 2 things. So this, once again, to make it like the density to be uniform over the whole thing. So if you thought of this pencil as having a uniform like density over it, then that's what you should think of here. Okay. And yeah, typically written as this like uniform thing. Visually, this is now the PDF. This is the density plot. And so to calculate something like, here's an example of a calculation you'll do. You'll be like, what's the probability that my random variable is less than some number C? That really means, okay, let me fix this slightly. You would write something like, let's say, greater than A, to be completely clear. Like technically you should know that this means, like the way I wrote it before, I didn't write this part here, but since this interval is up to A, you know that it means up to A. So okay. Yeah, let's leave it like this. But anyways, this means that the random variable belongs to this interval A to C, just as this like should be intuitively read. And the way you compute this is by using the PDF in exactly this way of like plugging it into the integral, taking the integral from A to C, evaluating it, and then so on. But like you get this type of thing, which is exactly the area under this region here. So that should be intuitively pleasing. And yeah, so in the tutorial, the assignments, you'll work things out. All you really need to do is just apply this formula. This is like what you really need to know for this stuff. Okay, some other common ones are this Gaussian, or sometimes called the normal distribution. This is really classic and covered everywhere. The interesting thing is that, okay, so it has 2 parameters. This thing is called mu and sigma. They have English words, like names to them, and this is called the mean, and this is called the variance. We'll cover that later, what that means. But the interesting thing is that this PDF of a Gaussian is actually this very complicated looking function. So like, look at this thing. It's got like, it's a whole mess kind of. It's like this exponential. It has all these things in here. It turns out that this thing, which is the PDF, right? So like, what have I plotted here? What I plotted here is P, this P function. It has this really nice shape, which some people call like a bell curve or something. And so here I plotted this black thing is like the example there. So it turns out that this is the peak point. Why is that the peak point? It's because this input becomes 0 at exactly mu at the mean. So then you just get exponential to 0. Anyways, you get this point here. The thing I just wanted to highlight very briefly is that this sigma parameter, sigma squared, is called the variance. And the way you should think about it is if you make the variance small, and it's exactly as the word would say, if you make the amount that the distribution varies small, then what do? You get a distribution that looks like this, that has low, like it varies, it doesn't vary that much over the outcome space. And if you make sigma squared big, which means you make the variance big, you get a distribution like this green one, which means that the outcome space, like the probability of getting any outcome is wider and it kind of varies more. This is going to be the intuition. you have of these things, and yeah, it's sometimes written like this, it's sometimes written like this, similar to before. Okay, and then finally the last one you're going to need to know is this Laplace distribution. And so we're really covering the ones that are going to be used in this course. So this is the last one. So this Laplace distribution, and the way you think about it is it's almost the normal distribution, except with some slight changes. So just to compare, the normal distribution had something like this random variable. Well, okay, here it's like a value in the outcome space. You subtract it from this parameter mu, and then it has this variance kind of term here. It's very similar, except like here you have this square term. In the Laplace thing, you just have an absolute value. So instead of squaring, you have an absolute value. That's like basically the same difference. This B thing is not quite the variance, but has like a similar relationship in the equation and everything. And anyways, the plot kind of describes everything, which is that the Laplace thing has this kind of peak shape. And the reason why, like another way to think about it, it's a double-sided exponential function. So normally an exponential function looks like this. And here, since we have the absolute value, we can actually talk about it from both sides. So when you have the negative one, it looks like this. And then the Gaussian just takes the exponential, but then squares the input. So anyways, this is what the two things look like. It's going to turn out to be, like, it's going to come up a bit later in the course when we start modeling things. When we, for instance, start modeling, let's say, like, what does the distribution of the price of a house look like if you say, like, we're going to use this word called conditioning on some features. So like, let's say if the number of rooms is 2, what might we think that the distribution of the price looks like? It turns out a classic assumption is to assume it's either Laplace or Gaussian. And each assumption is going to change the corresponding distribution we learn and how we learn it and things. But these turn out to be very classic ways to think of, like, yeah, you're going to want to model things like what is the distribution of the price given something and things like that. Okay. So these are the distributions we need to know. You can do calculations. You will do calculations with these kind of things. Okay. So now we move into the fun part, which is defining these notions of multivariate random variables. And like, yeah, what's the motivation here? So it's going to be able to talk about like the probability of like multiple different types of events. So yeah, you might want to talk about like what's the probability that I flipped 2 coins. Let's say I flipped 2 coins. So these are like 2 different things, like one coin, another coin. Then you want to say like what's the probability I got heads on the first coin or tails on the other coin. So for our data set case, which is actually going to be a multivariate random variable, we're going to say like what's the probability? Well, we're not actually going to end up like technically calculating things, but like you're going to think of the data set as like it's a random thing that has some probability of getting some house with some price as the first house, and the second thing is going to be like another house with another price, and a third one and a fourth and so on, up to n of these houses. Okay, so here's a bunch of examples in words. So you might think of the probability of getting heads and rolling a 3. So these are 2 random variables. The first one being like flipping a coin, the second one rolling a dice. Here's another one. The probability of a wine containing 2.5 milligrams of like the first chemical and then 4 milligrams of another chemical. There's 2 random things here, the first chemical and the second chemical. You might say, what's the probability of a house having 4 rooms and 2 washrooms and being less than 10 minutes away from a university? There's 3 random variables that we could use here, which is describing like number of rooms, number of washrooms, and distance to, what did I put here, from the university. This would be like a 3 random variables. And another one's like, the example we're actually going to use throughout these notes is going to be the probability of being young and having arthritis. This is the one that Martha chose before. It is kind of nice because here you can, there's some more like natural notion of what we're going to talk about is like dependence on things, which is like, maybe if I'm young, the probability of me having arthritis is actually lower than if I'm older. So there's going to be like these variables are going to kind of depend on each other. Turns out in supervised, okay, there's going to be some dependence in some cases in supervised learning, but okay. So let's define this thing. So we're going to think of a multivariate random variable as a tuple of more than one random variable. And so there was like some brief questions on Piazza about like, why do we call this data set a tuple and not a multiset? Technically, like a multiset is just a thing that you can have duplicates, but order doesn't matter. And so like the short answer is that a tuple, like the purpose of calling a data, like the purpose of calling it a tuple or a multiset is so we can have duplicates. And then the purpose of calling it a tuple specifically is because we're going to think of it as like this random variable. And all these random variables are going to be represented as tuples. And they're going to have this notion of like order, the first index is this random variable, and so on. And so it's just going to be really beautiful and natural to talk about data sets as tuples, because all these multivariate random variables are going to be described as just tuples of random variables. So it should just be like very intuitive and clean when we transfer. So here's some examples. You might write a random variable as like this: x equals to a tuple which contains two other random variables, x1 and x2. Okay. The first being like a flip of a coin, the second being a flip of a coin. And you can write the outcome space. The outcome space is just going to be every possible pair of the outcome in the first space and the outcome in the second space. And here you'll already see why we kind of like why this Cartesian product is useful. The Cartesian product of these, so this is the first, this is the outcome space of x1. This is the outcome space of x2, the second coin. And you want to talk about every possible outcome of both of them together. So that's exactly what the Cartesian product like is defined as. It's defined as the set, right? The outcome space is just a set. And now it's the set of all possible pairs. So this would be like getting tails and tails. Then you'd have tails and heads. And so you can see where this the Cartesian product, it just allows us to talk about every possible like combination of two things. If we had three random variables, you'd have the Cartesian product of all three. And then you'd have a set of all three possible things and so on. So very natural how that comes up. And okay, some other examples. You might be talking like thinking about, this is the case of collecting the info of exactly one house, and you care about, let's say, the number of rooms and the age. So now you'd have a random variable. Again, you use x. You have it has two. It's a very random variable to like a tuple of two, and here you would think now call this like the features. So the first feature is the number of rooms. That's a random variable. The second feature is the age of the house. That's a random variable. What's the outcome space? Well, here it's going to be the Cartesian product of the outcome space of the first one with the outcome space of the second thing, which here like number of rooms might be a natural number. Age of the house might be some number greater than 0, but it could be like 1.5, which means like 1.5 years, or 1.6, or pi, or I don't know. So hopefully you're already seeing kind of the power of like having these Cartesian products defined and having tuples defined. Things just started looking very pretty. Okay, so here's a slightly more complicated example of what this like feature label pair might look like. So imagine collecting the info of one house and its price now. So now let's look at the random variable. Your random variable might look like z, which would be this feature, this like random variable that itself is going to be a multivariate random variable, and the price. And so more explicitly, you write it like this. So this is the kind of the notation we've already seen, right? Here we have a feature, or like sometimes you call it like a feature vector. So it has, or maybe you call this the features, sorry. And then you have two features in there, right? Which is the number of rooms and the age. And then you have a third random variable, which is the price. And so you can see you can start like combining these, like nesting them and things like that. And the way you'd write the outcome space is kind of as you would expect. You first write the outcome space of this random variable, which we've already written before. That's just this Cartesian product. And then you put brackets to like make it clear that that's like that's this set. And then you take the Cartesian product with the price, which is the values the price can take. Okay, so this is our outcome space. It's like this thing is a set, right? The Cartesian product is a set. And so like, yeah, maybe just one note is like in the tutorial, I'm going to try to go over like a bunch of like these examples of like Cartesian products are sets. What do elements of the Cartesian product look like? They look like this. So this thing would be like an element of this set here, right? Which makes sense. This is the outcome space. It's a set of outcomes. What is this random variable? It represents like one possible outcome. Okay, so like this would be the example where your data set contains n equal to 1. So you have one feature label pair. The only thing that's missing is now just imagine like chaining this with more examples and then making it a big tuple. Okay, we're gonna see that. But let's see. Yeah, I think we can go through this and then end. So finally, how do we calculate these joint probabilities? It's going to be exactly the same way as you might expect, which is that you're going to use a PMF or a PDF. If everything is discrete, you use a PMF. If everything is continuous, you use a PDF. And if it's a mixture of both, it's going to get complicated. And I'll go over one example, and yeah, you'll see what happens. But just for now, like most things you see in probability courses, you just assume everything's discrete, and then you do the thing. Okay, so how would that look? Imagine we have this random variable, which is now just like that's two indices, x and y, being like, so okay, so we have this arthritis example. The first random variable is going to just describe like if someone's old or young. It just has a binary thing, 0 or 1. So 0 means young, 1 means old. Yeah. I think okay, let's end it here because I think I might have used young as one throughout the thing and then old as the other. So I'll just fix that later. Okay, so let's end here, but yeah, we'll continue next class. Thank you.